So this is the third lecture on the closed form solutions for the harmonic oscillator, and in this lecture I will apply the results that we had in the previous, actually in the first part of for the solutions of the harmonic oscillator, and apply those to the series RLC circuit just to demonstrate their application. So here is a sketch, as I admitted in the written lecture, stolen from the internet, for an RLC circuit. So what do we have here? We can figure this out. It's not bad. We have a resistor which provides a force that's kind of similar to friction, right? And you think of a mechanical system. Here's a storage capacitor, call this a capacitor, and here is an inductor. Okay, these are positive constants, positive non-zero constants in this case. If you have more advanced electronics, then you end up with something quite different. You can have different kinds of active resistors and all kinds of different circuit elements, but we're using just the basic ones, R, L, and C. And here's a driving force. It would be like plugging it into the wall or connecting it to a battery. That's what goes there. Now we're going to take Kirchhoff's voltage law and we're going to turn this into a second order differential equation that's in the form of a harmonic oscillator. So this voltage law says that if you add up all the voltages here around the circuit, they're all going to sum to zero. So here's an applied voltage is going to be equal to the voltage drop across the resistor, the voltage on the capacitor, and the voltage associated with the inductor. And we have formulas for these. The voltage drop across the resistor is just the resistance times the current that's flowing around the circuit. The voltage in the inductor is the value of the inductor, L, times the rate of change of the current. So now you see where the differential equation is going to come from. And then the capacitor voltage is charge over capacitance, but we have another continuity equation that will also turn this Q into current. So what I'm going to do right now is rewrite that equation in terms of the current. Later in this lecture, kind of as an aside, I'm going to show that you could have written it in terms of the capacitor voltage or in terms of charge. Okay, you get a different you'll have different variables, but actually the differential equation will be essentially the same. So I start with this equation that relates current to charge. Current is just the rate of change of charge. Okay, I'm going to take the same differential equation here and I'm going to differentiate the whole thing again. I'm going to set this to 0 because I want to do only the homogeneous case. So taking another derivative, assuming L, R, and C are constant, this becomes and then I get R times di by dt, and now I have 1 over C times dq by dt equals 0, and I say derivative with respect to time is current, so I plug that in. Of course I get second derivative here, first derivative here, and just the current here. And now to proceed I need to write it in standard form, so I have to divide by L. So this becomes R over L, and this becomes LC, and then of course it doesn't matter on the 0. And so here is that equation for the voltages around the circuit, actually expressed in terms of the current, in written in the standard form. And immediately we can see that R over L is what we had for P in the standard form, and the Q, 1 over LC, is Q. We're going to get a characteristic polynomial. It will be, you could write it in terms of P and Q, or you could write it in terms of R over L and 1 over LC. Okay, I did that here. Here's a characteristic polynomial that we had from the first lecture on the closed form solution for the differential operator. Then I substituted in here and this term gets rearranged. If you pull the 1/2 under the square root sign, then you can write the condition on the roots for the characteristic polynomial in terms of r over 2l squared minus 1 over LC. This is very convenient because here's the 1 over the r over 2l sitting right out here. Right, so you're using the same term again, and so that's a more convenient way to write it. At this point you could say, well, now I can solve all those cases again, the overdamped, critically damped, underdamped, and purely oscillatory. But why bother? You already did it. And again, I'm stressing in my teaching of this class that when you solve things using variables in a very very nice manner, very abstract manner, then you're done and you never have to solve the problem ever again. All you do is evaluate your results in any way you want, and that's exactly what we should do in this case. Why solve it again? We've got it. And then you can put in whatever numbers you want when you're done with that. So at the end of the written lecture on this subject, I had another chart for the series RLC circuit, as we discussed here, giving the conditions on the for each case, overdamped, critically damped, and underdamped, and then writing the roots, which I'm calling alpha, if it's real, the real part alpha and the imaginary part omega, writing them in terms of the parameters from the RLC circuit. I didn't write the initial conditions here. I kind of left them vague because there's no reason in this class to get into how to measure things in the lab. And I can't claim to be much of an expert in that anyway, since I'm a theorist. Okay, so here are your solutions. This gives you the current. The interesting thing here, of course, is that we call them harmonic oscillators, and you think they're all going to oscillate. They aren't. Some of them are overdamped and they never oscillate at all. The critically damped kind of start to oscillate. The underdamped oscillate, but in a exponentially decreasing, with exponentially decreasing magnitude, and only the purely oscillatory actually really oscillate. And here's some of the rest of the solutions, and now we can make the identification. What is a resonant frequency for the series RLC circuit? It's 1 over the square root of LC. And now we know the resonant frequency for this circuit because we did it again using variables. And this attenuation, although it's a little more complicated, for the underdamped case, the attenuation is R over 2L. Okay, so it's not just the resistance, note it, it's also the inductance. That's kind of interesting. So here are 3 plots of these 3 cases. And I took these from the internet instead of drawing them myself by hand here. Okay, well, that's what I did. Right, so here's the underdamped case. What's the envelope? The envelope is e to the minus alpha t, and you draw 2 of them to create an envelope. Really, the e to the minus alpha t is just sitting right here. It's decaying. Okay, as you know, actually if you write e to the alpha t and let alpha be negative, you'll have the same result. Just depends on how you want to write alpha. Okay, and here's the oscillations that are coming on in between it, and they're asymptotically approaching 0 in the underdamped case. For the overdamped case, there are no oscillations. It's just going towards 0. Critically damped case, start with a cosine term. You might see it kind of go underneath, come back up, maybe not even quite that. And here it's a sine wave, so you see it starting to make one oscillation and then damp out. So here's your critically damped case, overdamped, and your underdamped case. Now, I just wanted to show that you would get the same equation no matter what the variable is for this circuit, the same parameters for the attenuation and for the resonant frequency. So here's the differential equation that we started with before, just from Kirchhoff's voltage law, and of course we have the homogeneous case, so we don't have a battery and we don't have it plugged into the wall or there's no voltage, applied voltage to it. Now I'm going to use again the definition of current as a rate of change of charge, and I'm going to take the second derivative then of charge will be the rate of change of current. I'm just taking another derivative here, plugging this into the equation. Okay, plugging these into here, I get the equation for the circuit in terms of charge, the charge on the capacitor. When I write it in standard form, look what happens. The P is the same and the Q is the same. The attenuation is the same and the resonant frequency is still 1 over the square root of LC. The characteristic polynomial would be the same. And will happen also if we use voltage. So instead of using the equation for charge, I'll use the one for voltage on the capacitor is charge over C, charge over the capacitance, so charge equals capacitance times the voltage. I can take the derivative of charge, the second derivative of charge here, ended up with derivatives of the capacitor voltage, substitute that in, and I end up with, here is the standard form for the same circuit written in terms of the voltage on the capacitor. And we see, again, R over L, 1 over LC for P and Q, and the same for the attenuation, and the same form for the resonant frequency. Now in suggested homework, I suggest you go through the whole exercise again using the mass and spring system. So let's look at that for a minute. So in the mass and spring system, the easiest way to think about this is you have kind of an immovable wall and you've got the spring. You've got a mass attached to it and the spring is not moving. And then you displace this mass, you pull on it out to here and you let it go. It's going to be sitting on some kind of a table that has some sort of friction associated with it. There are other ways to do mass and spring. You can have them hanging down, you can put two masses on either end, and then you end up with things that you might get in quantum physics later on. But we're just going to use this one right here. And any motion you have, you can start using Newton's laws. So force equals rate of change of momentum, of course, but because the mass isn't changing, we can just write mass times acceleration. So that is, the second derivative of the displacement. S of t is displacement. Now Hooke's law says the further you pull it out, the bigger the force is trying to get that mass to return to its equilibrium position. And this is Hooke's constant. Of course, this doesn't always work. You can pull the spring out so far that you spring the spring and break it and pull it off the wall. So all kind of things can happen, of course. But within certain parameters, you can say that the restoring force is it's negative because it's pulling that back in towards itself. Okay, towards the equilibrium position, and K is just a constant. Now there's a damping force, and that has to do with the friction here. There's different models of friction. In some cases friction goes as velocity, which is what I've written here. It could go as a velocity squared. There's all different kinds of complications. But the way I've written it here is a typical way it is written in order to get a harmonic oscillator out of the mass and spring system. So let's go ahead and put those together. And we have mass times acceleration equals minus k minus beta. And there's no other force on it. We don't have something that's a motor that's continuing to move the mass around. So we can write all this in standard form. Well, first we'll write it all on one side. And now if we want standard form, we want the coefficient of the second derivative to be 1, so we divide by mass. Again, mass is strictly greater than 0, and so is k and beta also. Okay, if beta happens to be, I should write beta is greater than or equal to 0, because if it happens to be 0, then that's where you get the purely oscillatory case. And now we have the same situation we have before. Here's our identification, beta over m for P, and Q is K over M. So immediately you know that the resonant frequency for this mass and spring system is a square root of K over M. And you can work this out. You can go through the steps, or you can look at the solution that we derived before and plug into it and get all your solutions. So in some cases, depending on the values of the parameters, you're going to take the mass here, you pull it out, and if it's an overdamped case, all it's going to do is kind of go back asymptotically to its equilibrium position. This would be overdamped. It will never oscillate. The critically damped case, it will try to appear to try to oscillate once, but it's pretty much going to just go back here. And for the, this would be critically damped. Okay, for the underdamped case, you pull it out here, it's going to come back about the same amount, but every time it comes back, it moves less and less of a distance from the equilibrium position, and then finally settles down asymptotically, of course, to the equilibrium. And then in the purely oscillatory case, it just keeps oscillating back and forth because there is no friction or any other damping force. So in this case, you can write the constants in terms of the initial conditions. So you have S at times 0 would be S naught. That's would be the where you let the mass, your first displacement of the mass. This is when you start the experiment. You've pulled it out. You don't start it at equilibrium. It will go nowhere. Okay, and then the derivative at 0 will be S prime at 0. That might be 0 if you just let it go. If you let it go with a little push, then you might have S prime of 0 to be not 0.